Well, I want to continue on in section 3.3 here and talk about the use of the calculator to help you solve some of our engineering problems. So each of you should be in possession of a scientific graphing calculator, and one of the tools on those in those calculators is the solver. Obviously you can do some graphing as well, and the other thing we're going to talk about is doing some linear algebra on your calculator. All of those tools can be used for your benefit, or can be used by you for your benefit for solving homework problems and exam problems if needed. This doesn't mean I don't want you to know how to do the algebra, but this is a course, and your career will be based on knowing what tools are available and what tools are okay to use. In this course you can use the solver. So here's a problem that 313 here, where we have a weight, 3 weights actually, and let's just go ahead and put them on here. This one says this one weighs 275 pounds, this one weighs 300 pounds, and this one is a mystery, and this angle theta is also an unknown. Alright, the system is in equilibrium, and our objective is to find out how much the block C weighs and find that missing angle theta. Alright, let's draw a free body diagram. So I'm going to move this up a little bit and draw the free body diagram here. The free body diagram that we care about will be this point right there. Well, let me scoot back in a little bit and just talk about the way this problem is constructed. We have a knot right there, and we have 2 pulleys. So the pulleys, you understand, is that the tension in here is going to be the weight, and it's going to go around here, so the tension here is going to be 275 pounds pulling away from that knot. C obviously has a pulley here, so whatever this weighs, that's going to be the tension pulling away from the knot in that direction. So the point of interest will be that knot. So let's go ahead and draw that. So here is our free body diagram. I have C going up this way. I got 275 there and 300. And let's draw the components of the forces. C cos 30 and C sine 30. 275 cos theta and 275 sine theta. Alright, again we'll call that the x direction by convention, and the y direction will be going up like that. Alright, let's sum the forces and see what we get. If I sum the forces in the x direction, I guess I can just do it like that. I have negative 275 cos theta, C cos 30. Those are the only forces in the x direction. Sum the forces in the y direction. I got that 300, 275 sine theta, C sine 30, and I get this equation. Substituting this into here, I get this one equation right there. So you can see that there's an equation that has a sine and a cosine in the equation. That's a little hard to solve unless you have some modern techniques. So the modern techniques I want to talk to you about is the use of the solver. So let's just talk about that real quickly. I'm not going to show you how to use the solver in this video. What I want you to do is refer to the document that's in the course resources on Blackboard, and it will talk about how you set up and go through using solver. When you do that though, you'll find that there is an angle right here, angle 40 degrees, that probably will show up first, and on the next slide I'll show you that one. There are actually 2 solutions, and so you need to search for another solution, and with the graphing technique you'll be able to see obviously where those 2 solutions are. So let's go to the solver solution first. So again, if you look at Blackboard, you can see how to use the solver. But so I'm not, again, this video is not intended to teach you how to use the solver, but to show you that it's powerful and that it is important and a good tool for you. So this is the problem using the solver, and what you do is you make sure that the solver is set equal to 0 in using the TI-83 and 84. TI-89 is a little more powerful, and Inspire is a little more powerful. You don't have to set everything equal to 0. But basically you set the equation equal to 0, you hit enter, it takes you to the solver routine, then you hit alpha enter, which is alpha right there, and then enter, and the answer will show up right there. Alright, to get the other answer, you would have to seed this. You'd have to put a fake number in here, something greater than 50 degrees or 80 degrees or something like that. The way solvers work is they iterate from negative infinity to positive infinity, and it's going to come up with the two closest answers to wherever it starts. And I'm not sure exactly how all of the algorithms work, but often if there are two answers, you'll only get one of them to start with, and you have to search for the other one. Alright, let's look at the graph. This is using a graphing program that I downloaded on my computer, and it's called FromGraph.com. It's really easy to use and very powerful again. But here, with the graphing technique, you can see clearly where the two roots are, and those are the two answers to our equation. So what you do is you set up the y function as a function of x, and I've set value here is equal to, well, it's just the y, and then on the x-axis I put that is in theta in degrees. And so here again it shows you where the intercepts are, and those are the two solutions to the problem. Plugging either of those back into our equation, you can find out what the value of C is, and C, you have to go back to the other equation, sorry, and you can find out what the value of C is there for those two values of theta. So anyway, those are two real handy techniques for solving difficult to solve kinds of problems with sines and cosines in the same equation, and I encourage you to master one of those things. Here's another type of problem. This doesn't have sine and cosine in the same equation, but it is kind of a tedious algebra problem. I just want to walk through this with you. I believe I'm going to assign this for homework, so you get a chance to actually practice this exact problem on your own. The solution is given here, but what's going on is that's got a knot right there, and those are two knots or pins. I'm going to pull it this way, and the ball here is going to be hanging freely, and the hope here is that what we want to have is determine the forces in those two cables to hold this ball in equilibrium at those angles. Now those angles are given where D here is equal to 1.0 meters. So every other distance is given, so I solve for those two angles, theta 1, theta 2. Draw the free body diagram. I got a free 300, got an mg, got some sines and going up here, cosines going that way. By now I hope that you're able to walk through those things pretty quickly. And when you get this, you can see that some of the forces in the x looks like this. Some of the forces in the y looks like this. And I've solved this with algebra, but it's tedious, and that's why I say that if it's a linear or two linear equations, a set of linear equations, you might find the use of linear algebra helpful for you. So I'm going to show you how to solve this using RREF on your calculator. And again, I'm mostly referring to the TI-83 and 84 since those are the least expensive ones. But when I use RREF, I should be able to get the tension in AB is 99, the tension in AC is 265.9. So let's go to RREF and look at that. So if you were to, so again, what we're looking for here is if the equations are in a linear form. That means you can't be solving for a sine or a cosine or a squared function or anything like that, but if it's in a linear form of ax plus by plus cz is equal to k. Now this is actually just a two-dimensional problem, so all we're doing is ax and by is equal to some value k or some variable d. If it's a linear form, then you can put it this way. So here's my equation from before. Ax or AC plus, I took this equation and simplified it just a little bit, and so then what I got is that. The y equation, I said minus mg, and so I'm going to use this. And what we're doing with the RREF is we want to put the coefficients of the variables. What I'm looking for is AC and AB, so the coefficients will be this and this. And this equation, there's my variables, or what I'm looking for, and the coefficients in this case would be 1, and this would be the coefficient. The constant basically goes on the other side of the equation, onto the right side of the equation for RREF to work. So I just plugged it into RREF. And again, I'm not teaching you how to use RREF, only to show you that it is powerful and valuable. And when you do that, you can see that AC looks like that and AB. So all you're doing here is in the RREF form, in the matrix in the calculator, you put the coefficients of the variables into that form. Now just pay attention to this portion right here. What I want you to do on an exam and also on your homework, of course, if you use RREF, make sure you write out the equations in the form that you're putting into the calculator. That way I know that you know what you're doing in the way you're using RREF. So put the sum of the forces in the x equation and then put the coefficients. Sum of the forces in the y equation and put the coefficients. And again, refer to the documentation to figure out how to use RREF. Well, this next problem isn't the use of the calculator or solver, but it is to just show you that sometimes other techniques and other identities can be helpful in solving some equilibrium problems. But let's look at this pulley knot arrangement. There's a knot right here and a pulley right here. We know that the weight here causes the tension. The tension is going to be the same right here as right here. And what we're looking for is the tension in each of these chords. Well, we already know the tension in this chord is equal to that, but we're looking for the tension in this chord. But if we look carefully at the problem, what it is the pan here, this is kind of a scale, the pan here has a mass of 2 kilograms. The counterweight here has a mass of 10 kilograms, and we're looking for how much weight is supported here. In other words, the mass of that weight D. So we don't have to go through the whole problem in detail. What I want to do is show you how to set it up. If you recognize that there is a length here that's given and a length here that's given, you should be able to understand that how to find the angles might come from the cosine law. So the cosine law says that I think there's also another clue here. It says that the string here is equal to 2 meters long, and it gives you a a distance here. So if you know that distance, and you know this distance is 1.25. What we're looking for again is some information about the angles. And you can use the cosine law. It looks like you could probably use the sine law as well. But I use the cosine law to find out what alpha is, which is right there. Then I can say that because this is an isosceles triangle, I know that these two angles are equal to each other. I know there's 180 degrees on the inside of a triangle, so I can find out what beta is. Once I find out what alpha and beta is, then by parallelogram rules and parallel lines rules, we know that this angle alpha is the same as that angle alpha. This angle beta is the same as that angle beta. Now we have enough information to draw a Freebody diagram. So let's go ahead and do that. We know that the tension here is given, and it's going to be the same tension as pulling away. Now that I know alpha and beta, I can do the cosine alpha, the cosine of beta in the x direction, the sine of alpha and the sine of beta going in the y direction. The weight going down will be the d, which is the weight that's being suspended, plus 2 kilograms times 9.81. Some of the forces in the y direction, and you should be able to solve that for the mass that's being suspended. So anyway, I hope that is helpful in some of these sometimes a little more difficult types of problems to set up. And the last thing that I want to do in this section of 3.3 is just to help you understand what the difference is between some problems and other very similar looking problems. For example, here is a weight being suspended by 3 ropes. It's got a knot there. It goes back up here to another knot. In this case, we should, if we wanted to find out the tension in the ropes, all of the angles are given here. So to find out the tension in the ropes, start here. Move to here, find those two guys. Once you find this tension, move to here, and then you can find the tension over here. So those are pretty straightforward. A very similar looking problem would be something that might have a pulley here. In this case, again, you're looking for the tension, but the tension here is going to be the same from A to B to C because of that pulley. So that's going to be the same tension in this cord as that cord. Again, start here where the weight is, go down, you can find those two guys, move up here and find out that. And here you don't know the angle. The angle is a little more difficult. Well, it's not difficult to solve for, it's just not, it's not 30 degrees. I guess that's what I'm trying to communicate. If that's a pulley, this can be in equilibrium with an angle of 30 degrees. This one would not be in equilibrium if I specified that angle, so you have to solve for that angle. This other one is again similar. This is actually the textbook's problem where there's a pulley here and a pulley here. In this case, it's a counterweight as well. If this mass is given and these angles are, if that angle is given, you know that that angle is the same as that angle, and the tension is going to be the same in all 3 cords because of the pulleys. And some of these cases you may be looking for the mass, maybe you're looking for the weight, or I'm sorry, the angle or something like that. This is a very similar problem over here, but instead of a pulley, I've got a knot or a ring. So again, because that's a pulley, I know the tension is going to be the same over here, but this tension is not going to be the same as that tension. So I hope that those are familiar and easy for you by now, and we will do some homework and practice this stuff.